Hello everyone, how are you all doing? Am I audible? I'm assuming I'm audible. Yeah. I think we should start. I think let's start. Um, yeah. Let me share my screen. So, any of you started your project? Did you get time to actually look at your project? Not yet. No, understandably. I assume that, um, you know, so let me first. But I encourage you to start it. Just don't keep it for the end of the session. uh, I think you'll still get some good time to complete it. But what we can do is that we can discuss the topics, isn't it? And if you have any questions, we can discuss that. I strongly believe that the questions that you have, doubts that you have, we can actually clarify in a session much better. Yes, I think on Monday it's gonna be mostly open house, all of Q&A. We will not have you know, in sort of an agenda to go with. Maybe Monday is something that we can utilize all the queries on the things. Um, okay. Yesterday was heavy, is it? I think, how was your session yesterday? I think overall, now that you have understood all of neural networks, I think not all of it, I think the fundamentals of neural network, what we are now, moving across is, specialized networks, right? We will see, we will actually try to get an intuition on why and what. Computer vision is a separate course altogether, but I think it's a good effort for you to understand what does this architecture of CNN brings. Yes, yes, absolutely. You can discuss any kind of things. Yeah, anytime. Absolutely. See, we will have time. Okay. So the thing is that if you actually let me actually share the learning plan and let me open the self-learning ones. Okay. And if you see that, right, we are in lesson 6, right? And we have lesson 6, lesson 7. Lesson 7 will be a little involved. So the good thing about is that we will not be touching NLP because it's not part of the course, and we'll be mostly focusing on the time series. There is an NLP practice project on sentiment analysis, right? So it still will not be that much heavy, So we should be able to, finish 6, 7, 8 in a reasonable time frame. So and then we can have lots of questions. So we can ask, go back to from where we started and bring up any topic whatsoever for an open house discussion, right? Okay, so this is CNN, and we have introduced ourselves to this architecture, and but we still don't understand that why we need CNN, right? Did you guys understand why we need CNN? I mean, till now, you are saying that we have this, neural network, neuron-based, biological neuron-based system, which is clearly doing a great job, right? What was the key difference between a neural network versus a logistic regression? We had a question yesterday, and we went through this. Can anyone answer that? What was the, okay, yeah. So I mean, I wanted a feature selection. Okay, so neural network does a feature selection, but if you want to quantify something, do you remember our network, the network that we went with? What was total number of coefficients? Do you remember how many coefficients the logistic regression would have been returning us? Yesterday we went through this, right? We had 4 features, right? Sorry, 8 features in one of our problem statements, isn't it? In the diabetes, there was 9. And how much was the network giving us after adding batch norm, dropout, 3 layers, and and many of these things. How many total number of weights and biases that we had? Remember, total number of weights, the diabetes test case, diabetes practice that we have. It was running in thousands, isn't it? And in fact, after hyperparameter tuning, it went to 28,000. If you're not, do you remember that? Do you want me to show how much was the total number of this thing? Do you assisted service? So you can see my screen, right? So this was the thing, right? We ran it, right? And at the end, after doing all the great stuff, we did hyperparameter tuning. We went out to 100,000 total parameters, right? And this is like really deep neurons, right? So where was 9 and where is 100,000? It's sort of an overkill, but that's the key difference. The other key difference in the network itself, right? Do we remember what was the network? If you are using a logistic regression, you are learning 9 weights, 9 things, right? Generally, right? All these 9 things are related to what? There are 8 things which are related to features, right? And there is one thing which is sort of a global representation. That's about it, isn't it? Maybe a little bit more here and there if you add other types of parameters. However, in this case, we also not only we have feature level weights, we also have each sample level weights, right? That's what you connect each of the input to each of the neurons, isn't it? So that is also a classical difference, isn't it? Do you understand what I'm saying? Do you want me to bring that thing up, what I'm saying? So what I'm saying is this. Let me just try to, just to ensure that we all are in the, same zone, is that we are connecting each sample with each of the neurons. This connection, was it there in any of our traditional machine learning algorithms? Do you recollect? Actually, this is something that you should go back and check, okay? We all talk about so much about feature engineering, and lots of machine learning which focuses on traditional machine learning, at least linear regression, logistic regression. We are only learning coefficients for features. What about individual data points, right? So we didn't had any weighted sum or a sort of a weightage that individual data points brings, right? So this is also one of the key difference, right? Each of these data point, these are nothing but samples, are also connected somehow, right? So that's also was missing, isn't it? In a traditional. So there's a lot of things that you can ponder, and it will come in layers, but which is fine. What you should do is like encourage yourself to go down this rabbit hole again and again, so that you can you know um, realize what the thing is. Okay, great. So we've discussed what is CNN, and we discussed, sorry, we discussed the success stories of CNN. We discussed that the idea, what was the idea behind CNN, and Jan LeCun invented it and put it to use as well. The core idea of CNN was this so-called thing called as local connections, and then this idea of layering. Layering is that you learn in layers, right? You just directly don't learn faces, right? You learn in layers so that you can also generate or learn larger thing, and you have to be spatially invariant, isn't it? Any shape and size, any sort of transformation, visual transformations, we humans don't have any problem handling such things. Machine should not also, right? Any kinds of obfuscation on the image, whether you are blurring it, non-blurring it, as long as there is enough information, human beings generally don't have any problem identifying it. Machine should not also have, isn't it? So we also looked at some of the few popular neural networks, right? And we have gone till the time of 2017. The world has dramatically progressed in last 5-6 years, but the point is that these are the gravity defying models, and they have surpassed a lot of things and build a solid foundation towards it. We have looked into typical architecture. We don't know about them, I think by today we will know a basic idea of what a CNN is, right? This also is something that, so let me just go back to our explainers and we'll try to just give you some basic idea of what are we trying to handle, right? So we have worked it with MNIST for using quite a bit of 6, 7. I think we have most of our data was in MNIST. Only thing that I introduced was the diabetes data set, or else it was all about MNIST, right? And there was a reason for that as well, right? Images as a data type, do we understand what is images? Images are what? There's nothing but a data type, right? And we've understood that image is nothing but a bunch of pixels, right? It's basically a collection of lot of pixels. Generally, what we have seen in MNIST is basically only a black and white image. In other words, it's also called as an RGB. Okay, so the thing is that now if you actually represent the image like this, right? This is a classic way of imaging. It's in a matrix form, right? You can put an image like this, right? This is a 3 by 3 image. Essentially, it has 9 pixels, right? So maybe this represents, so till now MNIST has only one channel. This is called as channel. Essentially, this is a one set of 3 by 3 matrix. Okay, and this will represent only one type of color, isn't it? It's basically was actually presenting you either black or white. However, in case of a RGB, so this is a typical way of MNIST was representing like this. Remember that, okay? In a typical RGB, you will not have a one set, you will have one more set, okay? Understood what I'm saying? So this is one more set. So this will represent one more color, okay? This array will represent one more color and you will have one more color. So basically 3 channels, and this is called as channel. You should understand this, right? A channel basically means that this is nothing but this was 2-dimensional. So essentially this is a 3-dimensional data structure which represents channels, right? This is a very classic way of representing image. There are other types of functions also, right? There is a 4-dimensional scale which is also sometimes is good. If I'm not wrong, a lot of phones actually store in the 4-dimensional scale, okay, just to have more information, right? So this is something that we will that you have to understand, that this is how image is represented in a typical storage system or a typical computer. Okay. Any question? Any other? And generally each of these are all each of these pixels represents a value between 0 to 255. 0 indicates no brightness, 255 indicates brightness. Any kind of variations is nothing but it's various brightness, various combination of brightness makes red, green and blue, and a combination of red, green and blue makes you other different various, millions of colors, 7 colors or 7 to millions of colors that you have, right? So that's essentially what an image is, right? I hope it is very clear what is an image. I think by now you should be very comfortable with this, right? We represent image as a function, right? Can someone answers why do we represent image as a function? Why is everything is a function? Why do we need to? So this is how an image can be represented, right? It's an image. If you have to represent the image as a function, then it's some function of red and some function of green and some function of B based on what channel you are. But why function? Can anyone answer that? Why function? I think by this time we are, we understand it very well, right? Why do we need to present this obsessiveness of function? Why do we need everything as a function in a, no, but why do we need everything as a function? It's not matrix. Matrix is something that you can actually represent, right? Matrix is nothing but a data type. Perfect, right? Because you can actually remember that large big equation at the end of it's a loss of all the weights. You can actually do that, and functions, many other functions are by default derivable in nature, right? You can generate a derivative out of it, and machine learning is by virtue is an optimization. You're optimizing something, so you can optimize them at first rate. It's also important that functions allow you to create that compute graph, right? That computational graph, remember? And I strongly suggest you should actually go through that. Computational graphs are very important, without which it gets extremely, laborious to do this high-end operations, okay? Essentially with brag prop and all, right? So functions are fundamental. Everything, whatever you do, has to be a function. Simply just don't drop a static value. Ensure that you introduce a function. If you are going to create a new layer, okay, your own layer, right? If you are doing a research and you're going to create your own layer, you need to create a function and you need to ensure that that is differentiable, and then there is some weight, and that ensures that it doesn't, the function should only depend on weights to change its things. That is something that you should understand, okay, right? So why do we have this obsessiveness about images? Anyone? Because vision is a very, very key component to build intelligence, right? Eye is a mechanism to take input, brain processes it, outputs in many, many ways, right? So hence it's very natural that we will actually attack this vision problem first. Language is a little bit hard, isn't it? Because it has a lot of expressions, and it has very many various varieties of things. However, image is little, I don't know whether it's less hard or more hard. I think it is less hard, but it's equally important. It's not a solved problem. A lot of people are working on a lot of things, right? So I'm going to just give you a basic idea of things, okay? And what are we talking about, and then we'll come back to the slides and we will see that why it is what it is, right? So typical image filtering, do you understand what is this image filtering? We keep on doing it, right? You take a picture, you will do a crop, do the remove the bad parts of images, right? So we can do image filtering. These are very popular, some of the filters that we use, left, right, and center. All these apps, all these mobile apps that you have, they have filters, right? We do call them filters, isn't it? So sort of filters you can do smoothing, you can do segmentation, right? And so on and so forth. Now the question is that what is filtering? Like let's take this example. Okay, let us take this image. It's a image of a mountain and a tree and a river and a house. Okay, and this is a 5 by 4 image, suppose, right? This is not suppose, this is exactly a 5 by 4 image, right? You can do a lot of things with this. You can make, this is a colorful image, right? This is a, this is actually three, how many channels it will have? By the way, how many channels it will have? It must have 3 channels, right? So you have to have 3. Yeah, because so there has to be 3 in front of it. So you have one channel of black, one channel of red, sorry, red, RGB. You must have 3 channels. Then only you'll be able to represent color appropriately. But you can do this kind of filtering, right? Your any photo app open, you will see that you can do black and white, you can sharpen, and so on and so forth. These are the very typical use cases that is happening a lot, right? Isn't it? You can sharpen them. Can you find all the trees? This is a very common use case nowadays that we are seeing, right? Find all the trees. Do you think it's easy for a machine to find all the trees here? Might not be easy. It's very easy for us. We know what a tree looks like. We exactly know where to look in that image. It's basically on the left corner of the image. And not only that, we can even like in a very precise manner, if you have been given a scissor, you will be able to cut it appropriately, right? So for us it's a split second decision to find out a tree, right? For machine it might not be. And but this is kind of a use case is important, right? Find an object in an image, there is value in it, and this kind of problems is called as object detection. If you remember in the first course we have seen, right, that there's a need for this kind. This is also you need like check if it houses damage, right? If you see this kind of your when there is some sort of war or or hurricane happens, right? A plane might go and check what sort of damages have happened, right? And nowadays they are using a lot of computer vision technology to understand and gather information rather than going house by house. So that helps, right? So that is what it is exactly, right? So the hence image has lots and lots of information, and that we need to do. So we basically, so you can see that. So what you can do, you can use a filter to do black and white. You can put a filter to sharpen it. You can put a filter to find all trees. You can find out a filter which can check if the houses have damages and so on and so forth, right? You can make a filter to distort the image, make your face, something weird, and those are very popular nowadays, isn't it? So a lot of small applications are happening all across the image, right? So now the question is that if so now what is we use filters to basically understand various information patterns. Do we agree to this now? We are using this filtration operation, right? We call this filter in our world. We do call them filter, right? You ask anyone what is an image filter, ask any kid, they will know nowadays what is a filter, right? So in a way, filters are nothing but trying to find out some sort of information and patterns, and maybe changing the image also, isn't it? You are distorting the image, you are black and white it, even though the original image something was something else. So we use features to basically understand various information and patterns in the image, which can be said as features, right? One of the important problems that we have right now is that can you actually get from the image, can you actually say that this is tree, this is mountain, this is river, and so on and so forth? Very difficult, right? Very, very difficult, at least to do it in a human annotated way. I mean, I'm not saying it is impossible, but at scale it is pretty difficult, isn't it? So why can't we use in hand? Very obvious reason, right? You need a lot of man hour. ImageNet was done using hand, isn't it? There's also a lot of people who do it. And data labeling is actually a game, isn't it? So why can't we use, so to solve this kind of problem, if I give you a problem, please find all trees. Can you do it in using a classical machine learning like linear regression, logistic regression, or for that matter, SVM? Do you think you can do it? It's difficult, right? Do you think that it will be a good model that you will able to produce using a very classical machine learning kind of an approach? And why do you think you can't? It's because the data is dense. There's a lot of problems in data is not first, and also like we have seen the data is sparse, right? Most other places might be empty. There is not tree. The tree is not there everywhere, right? So it's only in some places the tree is there, and we don't even know how to model the tree. It's all just numbers, right? And some of the numbers might have ages and so on and so forth, isn't it? So why can't we do it? So now, okay, if I understood that we can't do it using hand, and maybe we can also, at least this class will be able to understand why we can't use a classical machine learning approach, because data is not linear. Data is not linear. It's a non-linear data, and you can give 50 different reasons for that, right? Few tree can be small, right? Few tree can be big, right? So that spatial invariance problem will actually come and kill and haunt this classical machine learning algorithm, isn't it? It is very difficult for you to model it. But question is that why can't we do it in a typical ANN? We did it, right? If you actually see all our dense network, we were doing all about that, right? So till now in our practice labs, we were using a classical dense network, dense layers, only dense layers, and was training MNIST. So what was the problem in that? We have to understand that. Okay, why we can't do it is something that why we wanted, even we invented neural networks, and but why is it still not working? Why will it not work for images? Because of this kind of problems. That because dimensional reduction, we have handled it, right? Now data is 2D input here. 2D-ness, you can always reduce to 3D-net, right? Remember, what we did, we flattened it out, isn't it? We have taken it and stretched the whole thing. You can also do that for you from a point of view of a computation. If every pixel is a feature, in our mind, it's easy for us to imagine tabular data. So if every pixel is a feature, what I did is that I flattened it out and I made every feature every pixel as its own column. That's what I did, right? So I can do that. Let it go to millions of features. I don't have a problem. But I know my dense layer will be able to handle it much better, right? So there must be something, right? Why was dense layer not effective, right? All of this, why you need a special kind of a network to find out. One of the things that it is that in dense layer, the number of parameters will become extremely large, right? Your dimensions, as you said, right? The number of parameters, the dimensions, even if it is not large, but feature generation becomes internally the feature generation becomes extremely difficult. Okay, and also because of those three properties of an image, typical image, right? You don't, for typical dense letter, all the pixels have same meaning, isn't it? But to understand tree, I don't have to look for everything else. This, so these are the important things that I have to do, right? So that is one of the reason that people felt that at least Jan LeCun felt that we need something else. And this is not a problem that uh, was that wasn't solved. They were solved in a different way. We'll see that how they solved it. Okay. So what they did is that taking an image, what they did, it's a very simple thing that they did, that they created literally something called as a filter. Okay. And this is exactly the same filter that you or any one of us in the world knows. Okay. Image filtering filter. Okay. Filter is nothing but another sort of small matrix. Suppose if you have a if you this is your RGB curve, you have one channel and 5 by 4 matrix, right? You have a 5 rows, so this is like 20 pixel we are talking about with one channel. So what we do is like we add something called as a filter, and filter is nothing but one more matrix. It's gonna be some number, okay? Right now we will not talk about what numbers are, and we apply this filter, and we'll actually go through this. What is this operation, okay? We'll just let's get the intuition, and then we'll actually detail it out. It's a very simple operation, producing very high density outputs, and it has changed the world of image processing forever. Okay. So what it does is that you take a small filter, you take a small 3 by 3 matrix, which is way smaller than the original image, and put it. It's like a lens. Okay, you put the lens in the corner in each of the pixel of the in that image. Okay, so basically this is what is this? This is 3 by 3 matrix, right? You put this 3 by 3 matrix. You consider this as a lens or a filter. Put it on the image and basically scroll through it. Okay, as a lens that you are going through each pixel by pixel, each row by row, and we will discuss this, okay, in detail. I have an Excel sheet. I'll show you now. Okay, via this I can show you how this operation happens. For now, let's get the intuition, and then we can discuss it, what it is. So the idea is that take this lens, which is called as filter, and scan through the image. Okay, while you are doing this scanning, do some operation in such a way, okay, so that whatever you understood from the scanned part of the image, put a new image out of it. So essentially take this filter as a lens, put it on the image, do some operation, and if this is your whole part that you are looking at, this will produce one single value, literally. Okay, and do this for the whole image in such a way that your value, this represents a very important information from the image. Okay, essentially when you look at the lens of a picture, you don't look at all the things, you only look at the important thing that you want to see. So the hope is that when you apply this lens, or this other way it's called as a filter, right, and do some operation, this operation is nothing but a simple element wise multiplication. Okay, when you do that, you will get an output of a number which will represent that part of the lens or that part of the image the lens or the filter has looked into it. So this number becomes an important thing. It sort of is a representational of the whole of that part. So and this is what we can continue to. And what has happened is that this this is this has transformed. This operation is is has what has done is that it has shrunk the image into an extremely small scale, but it has somehow somehow was able to maintain those three properties, like, its localness, its spatial invariance, and all the other three properties that we mentioned, it generally maintains that. What and how we will actually go through this, but this is the operation that happens. And the operation needs two things. One is an image that we will have anyways, and one is this lens, or otherwise literally called as filter, by the way. Huh? This is called as filter. In technical term, it is called as filter, okay? Which is like, it is again like a kind of function, right? You apply this function on the image to get another output. That's basically it, right? And we will see that what it means, right? So we can say that the filter function does something to the image. We don't know what that something is, which produces an output, and now the output can also be a function, right? So now that we have understood that why everything is a function, we will not harp on it. Now that we know that two functions will collide with each other, do some operation, and it will give one more object, which can be also represented as a function output. So this operation has almost changed the way we started looking at the whole image. What could happen is that this filter, this filter can be so small that it can actually look at the trees. You can devise a filter to look at only for trees. You can devise a filter which can look out for mountains. You can devise a filter which can actually look out for this rivers, and so on and so forth. Okay. So this operation has a name, and we'll talk about this operation name. But now we are all machine learning engineers, right? So we think that, okay, you have just dropped an idea called as filter, which is nothing but a matrix. An image is a matrix. Now, what are those numbers? First question comes to my mind is that what are those numbers that you can think of, right? And it turns out that if we want some output out of it, right, what are we trying to do? We are looking through the lens and try to reduce the picture in a way such that all the important information on that image comes out, right? This is exactly what we try to do in a feature engineering process, isn't it? That we try to extract information in a way that you can consider and then you can take it further, isn't it? So you can say that, okay, I will have a 3 by 3 matrix and apply in this 1 into 5 by 4 matrix, and I will have all the features as 0. But if you put everything as 0, right, zeros will never lead you to anything, right? You can have 1 will exactly give you the same set of values, right? But there are certain ways that you can think about it, right? Can I have a really big filter, right? Can I have a 5 by 4 filter? You can have it, but then basically you are replicating the image with image itself. So it's going to produce the same image, right? If you have a very small filter, like a really 1 pixel filter, then it's also the same thing, because your lens is so small that you are not able to, you're literally looking at the small part of the tree's edge. But that the problem is that then it might as well do it at a pixel level, right? Why do we need a filter, right? We wanted somewhere in between, right? So these are the intuitions you can work with and try to see that and literally, like, if you actually see the filters that you have in your Snapchat or Instagrams, they are filters with a specified matrix which you can apply on your image, and the images change. You can also apply on a video, and the video changes. Okay. So this is actually a very famous filter. Try it out. You can just create an image, read an image of MNIST, and just put this filter and try it out what happens. Okay. We will see some examples. We will see that how adding some filters do it, right? So in fact, let's see it right now. Okay. I wanted to actually run this thing, and you can see my screen, right? I've opened Google Colab because are based upon a token, or do we have any rule for selection? There is no rule. There are people who have actually started building features, these things. So there are, yeah. So the question is an important question. How do we actually select these values, isn't it? So there are static filters. Like, this is a very popular filter, by the way. Okay. There are other filters also which are more popular. You apply this filter to any image, something remarkable will happen. You know that, oh, this is how Instagram does it, or iPhotos does it, or Google Photos does it, right? If you want to make anything black and white, there is a static filter. Simply apply that filter, it will make everything as black and white. Okay, so there are a bunch of list of lots of exist static filters that you can use to change and morph your image and make an app out of it. That is not a problem. But the thing is that we are in the world of building neural networks, right? And everything antithesis is that we don't like anything static, isn't it? We want something else to happen. We want the network to learn these filters, right? And that is where this whole thing comes, that can you learn this filter in such a way, right? Is it possible for the network to learn the filter in such a way that I don't give a static value, learn given a picture that you can actually detect trees, houses, and so on and so forth. Remember that thing, that edges, faces, okay, and things like that. So that is what we will see. But yes, there are many such filters. In fact, if all the let me just open this. I'll show you some of the images. So the reason I'm actually going to Google Colab, because for some reason this SK image is not working in our practice labs. Okay. So sir, basically the basically values are basically intensity of values of what? No, we are not talking about weights and biases here. We are just talking about representing an image as a bunch of pixel values, essentially in a matrix. And we have one more matrix called as filter. If you apply these two methods in an element mine multiplication, okay, you do something, you will be resultant with a new output, which is nothing but another image. Okay, it will be another image, but it will change the image in some way. Okay, and this process of change, in this process of change, what happens is that you can learn those those important aspects of an image that you are looking for. Okay, and we will look into this. Okay, okay, it is image based on some static filters or some list. There are list of filters. Okay, yeah, of course you can apply in image a video. So what is a video? Okay, let's talk about this. So this was image, right? So this was image, right? If this is an image of 3 by 3, sorry, if this is an image of 3 by 3, right? So we said that an image or 3 by 3 doesn't make sense. We need, this was MNIST, right? And if you have to do color, then that means you need to have 3 channels, right? Isn't it? That's correct. So this will represent one image of an RGB. If you have 1000 images, what will you do? You will have 1000, right? So total number of training examples go in front of it, right? So this is basically, this is basically one image, literally, right? One image with 3 channels and so many pixels. Understood? So this is one image, right? So truly a image will be looking like this. One image of full value will be of 4 dimension. One will be representing total number of images, and this is your image, 3 channels and so many pixels. So every channel will have 99 pixels each, right? Right? That is correct. What, and in case, so this is number of examples. What will happen in case of video? Video is nothing but what is a video? Can anyone tell what is a video? Video is a collection of, what is a video? Yeah, but what is a video? Video is a collection of, it's a stream of images. Perfect. Every frame is nothing but an image. So you can, perfect, absolutely. So you can decide, right? 30 frame per second, 40 frame per second. That decides how many images you have in that particular frame, right? 30 frames. One frame, you suppose if you have one frame equals to one image. So video which is 30 frame per second can be represented as one video. 30 frames per second will be represented as how? So this is one video, right? 16 frame above becomes a video, right? So suppose this is a 30 frame per second. So this is one video for 30 frame per second. Are we able to understand it? So how we will do it? So this is 1x. Are we able to? So this is one video. This is one video of 30 frame per second having colors, images of RGB thing of 9 pixels. Are we able to understand? This is the dimension of one image with 30 frames per second. How many dimensions are we talking about? We are talking about 5 dimensions. Are you able to understand what I'm trying to say? So this is exactly how we can extrapolate. Whatever can happen in image can happen in frames, right? So videos are nothing but a 5-dimensional objects. Typically, one image can be represented as one color image is generally any images for that matter can be represented as 4 dimensions, right? So are we on the same page? Do you understand? So now if this is the case, you can actually have a filter apply on this as well. Okay. Motion is it doesn't matter to machine learning. So now, so one more time, right? So we have, okay. So if you have a black and white, so black and white, okay, BW. So BW has only one channel that we know, right? We have only one channel. We start with one channel, and we will say that it is 3 by 3 pixel. So which means that I have only one channel, which is a black and white channel, and I have 9 pixel, right? If I have an image of red GB, so then I will have 3 channels of each 3 by 3 pixel. Clear? Is that correct? Now if I have, so now I can represent like this, right? So if this means what? So basically one image of RGB can be represented as how? Let me just actually say one image, 3 by 3 pixel, right? The image is represented by 3 by 3, right? This is one image, right? No, that will come. That will come. So this is clear. This is 3 by 3 pixel. This is clear. This is the channel number and this is the pixel count, right? So one image of RGB pixel can be represented as 1 into 3 into 3 into 3, where 1 will represent, what will 1 represent? Total number of samples. This represents number of samples. This represents my channel. Second one is my channel. Third dimension is my, third and fourth dimensions are my pixels. Understood? So if you have to represent, 100,000 RGB images, what will you do? 100 images. Why 100,000? 100 images. So you simply say 100. Right? Right? So then you have, now let's expand this. So if this is what is, so one, there are 2 offs and, okay. So now one video, let's talk about one video of RGB. So we said that 130 FPS video of RGB, right? So this is one, and then we have to add 30 frames, 30 such images, right? Into 3 into 3 into 3. Is this clear? Is this clear? As long as it's clear, yeah. So this is number of images, number of videos, number of frames. Number of frames will generally represent number of images, channel, and pixel count, right? And this is how you basically your TensorFlow will see. And this is now you realize why do we need to work everything on Tensor. And this is the reason, okay? So let's do one thing. Let's quickly see what an image looks like. Okay, so I've told you, right, the reason. Okay, is this down? So the reason. So I'm just going to show you a few things. Okay, there is a library called SKImage. It's a very popular library. This is just to show you that what are the filters that you can do as is, like without anything. So there in this SKImage, we have coins. Okay. So you can load the coins. I am not interested in coins. So you can see the coins. What I am interested in actually is the coffee. Okay. So I have loaded this image. I just have to load the image from somewhere. Okay. So I just loaded it from here. That's it. Nothing else. So this is the colored image, right? Right. So if you actually see the image shape, what will be 400 into 603? Are we clear? This is as per our understanding, right? If you pass this image into a machine learning, you have to put number of samples, isn't it? That is important. Or else how will you know how many features will create, right? So how many samples will create, how will we know, right? So that n has to be there, right? Right? So if you actually pass this into a machine learning model. So this image shape is 400 by 600 into 3 channels. So the thing is that it basically for convenience, I have showed you like this. The channel is always on the last. Okay, that's for the convenience, is rotated, right? Now you can actually look at the 100th picture, check all the three channels at any particular pixel value. If you look at the 100 by 100 pixel, right, for all the three channel, you will have that particular channel has what, 139, 50 and 18 color, right? That is the intensity that you will have. You can actually visualize RGB channels, right? These are all very simple. Matplotlib already has this kind of things, right? And these are nothing but arrays, bunch of arrays, absolutely nothing else, nothing but normal matrices, arrays, NumPy array, literally NumPy array, right? Right? So now if you see, right, you want to see that particular image, get all my pixel for my 0th channel. So if you do this, you will see what? Oh, this is exactly what you will see, right? Do we have image? Yeah. So almost like a black and white kind of a thing, right? The first channel will look like this, and my second channel will look like this. Only my second channel. Okay. And if you, when you look all of them together, this is what you look, when you look all of them together, the actual color comes into the picture. This is my R channel. I think this is my R channel. Okay, this is my B channel. B will always be middle, like, and this is my RGB, sorry, G channel and B channel. Okay. Right, so I'm going to load one more data. This is called a checkered board data. Okay, one more image, some image, right? This is a chessboard, right? You can see that chessboard, and this is actually a so if I actually see the image shape, what is the image shape says? This is also a three-dimensional colored image. Like, it has three dimensions. It has three channels. Okay. So now what I'm going to do, I'm going to add a filter. Okay. So this is the filter. Forget about this term called as kernel. So this is the metric that I've spoken about, right? I basically, I have taken this matrix, whatever is come to my mind, I have just put it. I not it is not random, but consider that I have 4 by 4 filter, and I am just applying this 4 by 4 filter on my 400 into 3 into 600 into 3 filter. Okay, this is my shape. You guys agree to this, right? My shape is 400 into 600 by into 3. So I'm applying this 4 by 4 filter with whatever these values are, and if I use this function, we'll come to this function. This is what the function, that operation does. If you do this, right, what it happens is that it will, this particular filter only brings out horizontal edges, nothing else. Amazing, right? This is the operation that it's, and this is a very well-known filter to bring out only the horizontal edges, right? If you actually use this filter, okay, so this was horizontal edges, this is actually on the same image, this will give you vertical edges from the image itself. Do you see there is some value around it? Edges is good, right? Edge detection is a very important thing, right? If you need to know what is edge detection, right? If you apply this filter, look what happens. This is the edge detection. These are static filters. I have just, now these are very well-known filters. Apply this, use this function, apply on an image. It will literally tell you what are the edges, right? And there is value in learning all these things, isn't it? If you apply this filter, okay, on the image, you can see that what happens is that, okay, this is my original image. This is my original image. See what has happened? Can you guys see what has happened? Blurred. The act of blur can be easily achieved by this filter. Put and take any image, put this filter, you can make the filter, the image as blur. Now you realize what happens when all of these photo apps, what they do. This is what they do. Okay. And this is that image. This is one more filter. Basically, all it does, it masks things. You see, I've just applied it. Yeah, you can do portrait. There's hundreds of filters. Go to any of these mobile companies documentation site. Okay, just go to Apple, Apple filter. Okay, full guide on iPhone camera filter. But this is whose guide? This is not our guide. Our guide is how to apply. So apply convolution, right? Say this, and you should be able to, you should go to this developer.apple.com. You will see that hundreds of features they've already listed. Okay, and you can just go through this and just copy paste it, and there's a bunch of work, lot of work that is going on. Okay, you can actually build your custom filters also. That is what this Snapchat and Instagram people do, right? And they make a lot of ton of money. What they do is to find this filter which is intuitive enough in such a way that it is good. They normally not only do it using hand, but they can also use machine learning. Now you understood that using this thing like this is nothing but a filter. You apply on an image, you get various kind of output which is beneficial for you. That's very, very beneficial for you. Okay, understood? Get the idea, and we'll come back to this, right? So some more consideration. Let's have some more consideration. Some possibility, there are possibility that filter might be big. It might not fit properly around the edges, right? You have a really, no, you might not, it might be giving something else. Since the filter is moving, we might be able to control the jumps, right? It slides, right? So basically just like a lens, it goes here, 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 looks all of this. So all these filters are trial and error. Of course, at one point of them they were trial and error. Now, given the fact that you have Instagrams and Snapchats and all, do you think that it is trial and error? They will have a filter which they will IP it, isn't it? You can't even find that filter because it is so good, right? Isn't it? Because it's a very popular filter. So you put some prop on top of your head and so on and so forth, right? What are those? Those are nothing but a mechanism to join, give one image and another image, and generate one more image out of it, right? So, but our intention is that we are trying to find out. We are in the world of neural network. We are trying to learn things from image. We find out this filter operation is giving us ability to learn this kind of important features, and this is not the end of it. If static filters can give us some sort of information, right? So this is what we can do, right? So now, and so what do we call this operation, by the way? This is an operation we will actually now shift to. Okay, this operation is called as, exactly this operation is called as convolution operation. Okay, and you can convolve anything. Okay, this is a very, very important operation. It has started when the point when you are doing signal processing. Okay, signal processing was all about, there are a lot of signals were coming. How do you know you can actuate the real information out of the so much noise? So convolution is an operation. That is why it is part of signal processing rather than image processing. Okay, initially it was a very important technique to get out of get important information from radio frequencies. Okay, and convolution is nothing but a mathematical way of, okay, combining two signals to form a third signal. Okay, it is very important in DSPs. Whoever has run DSP in your engineering classes, you will have done convolution operation, right? You have learned convolution is nothing but, yes. So that's exactly the same operation that we are doing. Okay, so now in this case, what we are exactly doing is that, it's a process where we take a small matrix of number called as filter. Like literally, it is called as filter. Okay, a filter is nothing but a multiple kernels. Okay, there are two names to it. One is called kernel, one is called filter. Kernel is a single unit. Multiple kernels make it one filter. You can have multiple kernels, and each kernel can do a little bit of this, and hence same image will do a lot of other things together. Okay, and you pass it over an image and transform it based on the values of the filter. Okay, that is exactly what this idea of convolution operation is, what it does. Um, Everything is going over that. Okay. Yeah, I think you have joined, machine learning, deep learning. So I think this. But from an intuition point of view, we have even started mathematics. I don't think we will start the maths part of it in here. But do you understand the intuition? That is what is important, right? Convolution is what you understood. Convolution is an operation where you take one signal, or in this case, in our case, um, yeah, you have to revisit. So deep learning is, of course, right, it's going to be tough. So Python is a language, right? So convolution is an operation. You take a matrix, take another matrix, join them in some operation. That operation is nothing but an element minus multiplication, and you get a third image. Okay. How do you do convolution operation? Do you want to see how do you do convolution operation? Very simple. Let's go to Excel sheet. Okay. Favorite tool of a data scientist, right? What is the favorite tool of a data scientist? For a software engineer, it will be some language. For a data scientist, it's gonna be Excel sheet. Yes. Now someone told me that show this operation in Excel sheet, people will appreciate it. Software engineers in this group might say, "Hey man, no, we don't like Excel sheet." But guys, please bear with me. I think this conveys the point to a certain extent, so that we can actually go on with our studies. Okay. So now that we have, so we've understood the idea of convolution operation, right? What is that it's trying to do? Who wants to say what does it define? Forget about all those things. Tell me what is this operation's objective was. Our objective was to, given an image, I want to find the important information from the image. And the way to do it is that it is very difficult for me to actually do using manually. Not possible, right? Classical machine learning had a problem. ANNs also has a problem, though I don't actually now understand, right? All of us have still not gone through it. Maybe later we'll actually look into it. We find that this operation called as convolution actually has, helped a lot in the digital signal processing. Take a small matrix, apply an element multiplication on this matrix of images, and you get some output. And it so happens, if we choose these values properly, okay, if you choose these values carefully, this output can be really good. Now the thing is that since we are not building a snapshot application, we are building a neural network. So we will ask the neural network to choose a filter, right? We will say that, can you build a filter for me? Can you learn the filter while you are building, right? Not just hard code it, start from somewhere random, but can you learn the filter while you go? Because I have to optimize my loss function, right? So that's the game we are doing. So let's go back to my convolution operation. Okay, you can see my screen, right? I have shared a Google sheet. I'm showing a spreadsheet, right? You can see that, right? I think I'm sharing this. Yeah, same, right? Can you guys see? Can I get some yes? Can I? Yeah, right. So can you guys see my screen, right? I'm assuming that you are seeing my screen, so I'm continuing. Okay, if you are not, please let me know. So this is the image. Let's consider that we have an image which is 6 by 6 pixel. Okay, and we are considering one image. So basically, this is a one channel image, and I have a one image. Okay, we are machine learning guys. We are not digital signal processing guys. Our objective is that every time think of from a machine learning standpoint. So this is only one image having one channel but 6 by 6 pixel, right? And the pixel values are this. I have just randomly put guys, okay? I have no idea what this image will look like, but I've just ensured that it is between 0 and 255, ensuring that something is there. So as of now, what we are trying to do is like just trying to see what is this convolution operation does. So I have this 6 by 6 image, and I have this filter. Okay, it has some random values, right? So these two are there. So this value you can see this value. This value is nothing but a sum product of this filter and the highlighted part of the image. Are you guys able to see? Shall I increase the? Let me. I think this will be better. Maybe I'll increase a little bit more, right? 175%. Okay. I think this will be better. So now what I've done is that I'm choosing this, and to get this 275, there is a what was done is I've done a sum product. Sum product is nothing but element wise multiplication, which means 10 into 1. Yeah, I can share this. It's yeah, I can share it. It's not a problem. Absolutely. Okay. So 10 into 1, okay, 21 plus 10 into 1 plus 21 into 0 plus 31 into 1 plus 3 into 0, like that. This is called as element wise multiplication, and you can achieve it in Excel using this function called as sum product, right? Okay. So this, so if I what just happened, this filter when applied in this first part of the 3 by 3 matrix, it's not matrix multiplication. No, it's matrix multiplication was what we did in weights and biases. It is element wise multiplication. Matrix multiplication is a dot product, right? This is not dot product. This is element wise multiplication. How are we getting this? This is 10 into 1 plus 21 into 0 plus 31 into 1 plus 3 into 0. Element by element. Take this element, go to the image and refer to the same element's position, multiply it, then continue to add it. What will happen is that this will return me a scalar value, one value. This operation will return me one value. In a way, when I applied this filter in this first area of my image, I have got a value of 272. Okay, I have shrunk that part of image. You can think like that. In a way that I have got all the important information out of it and put it in this 272 values. Okay, all the important parts of my information is in this 272 value, right? So then what I do is like I move one row, sorry, not one row, one column. So 231 is, can you guys see this area? Are you able to see this area, this small area? Okay, I could not make this in some way. So just apply this filter. So I have moved my this lens or this filter one row, and I have this. It is beautifully fitting it, right? So that's what I do. Now that's not not the only thing that I do. I do the sum product, and after that I do an operation. Can anyone tell me what is this operation that I'm doing? I am doing an operation which is outside, right? What is this operation I am doing? Whatever value I am getting out of sum product, I am doing what operation outside this? Can anyone say? We just finished a very important, this is an activation function in neural network. What is an activation? Yeah, so what is the activation function? Very famous, max is not an activation function. We have a very specific name in the neural network for this function. No, it's not softmax. What does softmax is? Softmax, ReLU, good, great. Why ReLU? This is ReLU. Why ReLU? Because it's either 0 or more than 0, right? If it is negative, then it is 0. Max of anything or 0 is nothing but ReLU. Perfect, very good. Exactly. So this is nothing but a ReLU activation function. It's a ReLU activation function, and inside this, what is happening is a sum product, which is element-wise multiplication, right? If you did not knew ReLU, then or a neural network, this would have been a little difficult for you to realize. Okay. And now what I do is that I go to the next one, do the same thing again. You can see the filter has moved, and I continue to move it, right? And then once I reach to this end of this thing, when I got this, I have reached to the end of the image. Then I move down to my second row and apply this filter, and I continue to do it. So if you apply a 6 by 6 image, if you apply a filter of 6 by 6 on an image of, sorry, if you apply a filter of 3 by 3 on an image of 6 by 6, the convolution operation results in an image of or a matrix of 4 by 4. You have shrunk the image, and in a way you have represented the image in a nice fashion. Okay, your image is now very condensed. Okay, it's not sparse anymore. Okay, it has lots of important information. We don't know what this image might look like. Okay, that is for sure, right? Something like that. Correct. 10 into 1, 21 into this, 31 plus, and 3 into, yeah, that is correct. Perfect. Yeah, 100 into 1 and so and so. Perfect. This is called as element mind multiplication, right? So you can actually think about it. If you have a bigger filter, what will happen? Now from an intuition standpoint, I have a 3 by 3 filter which gave me a 4 by 4 image out of a 6 by 6 image. If I have a bigger filter which is 5 by 5, nobody is stopping you. You can add 5 by 5 filter, right? Who's stopping you? No one, right? So what will you give it? It will give me a much smaller image, right? So this is the exactly same convolution operation using a 5 by 5 filter on a 6 by 6 image, right? And it gave me a very small image on 2 by 2. Now, now machine learning in intuitions are kicking in, right? Oh, am I losing information? Right? You can ask that, did I lose information, or what just happened? Did you lose information? Do you think you lost information? What did you do? Did you lose information? Why do you say that? When you have 60,000, when you have 1,000 features in your input layer and you reduce it to 128 neurons, do you lose information? You are still reducing, right? Remember, you don't lose information. Actually, you lose. I mean, if you we filtered, yeah, there is a difference. That's a very nice word, that you filtered. There is a difference between losing information and filtering. You are trying to filter and trying to ensure that you collect only the good parts of it, and the rest you will come back later. But if you filter too much, you might actually be coming up with a very small data, which may or may not have, which may have lost more information, right? It is more condensed. So you need to be very aware of this kind of choice. If you use a filter of 3 by 3 versus 5 by 5, what happens? You have to be aware of it. Okay, and this operation is convolution operation. Now it makes sense. It's very simple, right? ReLU and then element size multiplication. That's all on every cell. That's all it is. Now we will start with this information, right? We will start with tuck 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 like this, and you can say that why is 1 and 0? We don't know, because we are in the business of teaching machine. What are the things that we'll teach? We will ask the machine to, can the machine find, this can be weights. This will be our default weights to start with, and we say that this is my sum matrix, please find my matrix. Not have a static matrix to start with or not end with. Please find my matrix. Can be anything. No, you put 5 now, what is there? I just showed you there was a 5, right? So if you see this, there was a 5 somewhere, yeah. You see this? You can see this, right? There was a 7. Right? If filter can be anything, doesn't matter. Right? But it has to be so I can change it. So it's just numbers, right? Remember, everything is a game of numbers. So that's number. However, if you want to visualize this as an image, do you think this is the right thing to visualize as an image? Can anyone tell that these numbers are, will this number make sense if you want to do a plot, pyplot dot image, wine, img show, or why? Perfect. So we have to be cognizant of that fact that it should not go out of that. No, I mean, it can go out as long as you don't try to visualize it, right? So remember that part, right? Not outliers, but the idea is that generally images will have pixel size up to 20 to 255, and we are seeing here numbers which are 355. So what does it represent? We don't know, right? It's a black box techniques, we don't know. What I wanted to, but let us try to emphasize on the fact that we are in the business of learning, teaching machines, rather than telling that that always go with this filter. Can you teach machine, can the machine teach itself these filters in such a way that it can get the best out of the image? That is the game. But convolution operation is exactly what we have seen. Okay, you can actually, this is a very simple convol TD. Okay, and in fact, someone was saying as OpenCV also has a convolve, lots of convolve operation. Every implementation has its own little bit of here and there. You have to be aware of it. Okay, but OpenCV also has all these libraries. Okay, extremely rich image processing libraries. Okay, they do all kinds of things. Remember that. Okay, and you can just implement it just like a function. However, this is a static filter, but we are building a machine learning model. Our objective is to build a machine learning model in such a way that I can find out extremely complex, hidden, latent features to classify whether something is a black cat, what, X, Y, Z or not, right? So that is a very important thing to do. Okay. So this is clear, right? Let's go back to our slides. We've forgotten the slides. Let's see. So this is exactly what we've covered in working CNN, and let's run through it and see where we are. So what is working as CNN? So CNN focuses on super small specific pattern than the whole image. Okay. If this is, see, for us it's so easy, right? If I show you, sorry, if I show you this image, you can still recognize that this will be a bird's beak. Human beings can still recognize. It is impossible for a machine to recognize, because how do you know that this is a beak? A beak is a classifying signature for a bird. You don't have a beak, we don't have a beak, lot of people don't have beaks, right? So the moment the beak feature is there, right, then that means already of billions and billions of types of animals in this whole world, there's only one type of animals who has beaks, right? So that itself, that whole segment reduces, right? So that is the reason that you need to be very feature oriented. But it is like, do you think that someone can actually, extract it and tease the message, annotate that this is beak? I mean, people used to do that. ImageNet was all about that, right? ImageNet was human beings were actually doing it, right? So CNN focuses on smaller. So C is that convolution. What is the full form of CNN? Convolution neural network. Convolution operation in a neural network. How can I learn? How can I do a convolution operation as a part of my network itself, right? Not outside, but as a part of my network itself. Can the can the network learn the convolution operation, right? Rather than giving the convolution operation, let it learn the convolution operation on an image. That is the important thing, and most important thing for that is this smaller region of, right, beak or maybe wings. Okay, thereby reducing this also reduces. Oh yes, 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 yeah. So we will see that. So that is exactly. But so as a part of your supervised learning, you can tell that this is bird of type. I don't know what is the name of the bird. Some bird name, right? And it can detect it. Of course, it can detect it. It can detect that it is not only bird, which type of bird it is. So if you see this, since you have asked, right? Let's go to our self-learning. Have you seen your assessment? Go to your assessment. You have a pet classification model using CNN. This is exactly that, right? You have different. So this is given pet images of correctly. So this is pet classification with a dog or cat. There is also a called as dog breed. Everything is dog, but dog breeds. That is what you're talking about. Which bird it is, right? So that is what it is. Which bird it is, which bird's beak it is, and based on how you train, you can do wonderful things, right? So what is a this is a very important thing. So like now you this filter, suppose you have found out this filter and you can name this as called as beak detector. It will do a aggregation operation. You understand this very well, right? And an activation operation. And we now know what is an activation operation that it does, right? Convolution operation by an Excel cell. What activation operation it will generally do? What is that it will do? Which activation operation will it do? So can you guys tell me what will the summation it will do? So if these two operation, if you have to explain what will the convolution do, what it will be? Summation will be nothing but, what do we just gone through? Which part of this is nothing but what will be the summation operation? We just saw it, right? We want to see that? Let's go back here. So summation operation is, this is my summation operation, isn't it? This is nothing but my element wise sum product. This is element wise sum, right? Understood? So this is my element wise sum. In my normal deep dense layers, what were we doing? We were actually doing a dot product of my weights and my inputs. In this case, I will do a dot product of my weights, which is nothing but filters, and with my inputs, which is nothing but my I will do an element wise sum of my weights and my input, which is my image, a part of an image, and then I will pass it via what function? What activation function will I pass it via? We know it, right? Overall, what is the activation function that we will pass around? ReLU. Perfect. Exactly. some element wise will taking labels. So yeah, think like that. I think you are already neural network trained. So think like that. It will just get easier and easier. Okay. So this is what exactly you do, right? And so we have large set of inputs. You have this beautiful filter, and you can actually go down to an output, and it can act as a this is exactly what we went through. What did we go? So we have this beautiful image called a 6 by 6 image. You multiply, you might have multiple filters. Okay, it's possible that you might have multiple filters. Nobody is saying that you will have to have one filter, right? You have three channels. You can have three different filters, right? So what I'm saying is that, so if you actually see this, like let's talk about this now a little bit. So you have this channel. Oh, we were actually, it was all there here. Okay. So this is the channel, this is the image, three channel image, right? And I have a cluster of filters, right? So we were talking about one filter, but this is an array of filters, right? I have one filter, two filter, three filter, four filters, which is applying on the image itself, right? And it is giving me a flattened output like this, right? So this is also possible. I can apply different filters on the different images at the same time. Nobody's stopping me. I can do whatever I want, right? This is exactly what happens, right? And each filter detects a small pattern of 3 by 3, right? And it makes sense to have multiple filters at the same time. You can say that why can't you look for only big? Look for big, feather, small feet, and so on and so forth. Things which flies and what. Right? At the same time, look at the various different types of features, right? And then what we do is like we shift. So we discussed it. What is the purpose of the filter? What is the purpose of the filter? Filters, if you apply a filter, anyone wants to answer that? Why did we use this kind of a filter? A filter is nothing but a lens. A filter will allow us to extract the features, right? So let's go back to that operation. Right, let's go back to this image. We added this filter, right? We applied this filter. Remember, we have taken an image and we applied this filter, and we've got the edges. We have taken the image and we've got the vertical edges. We have taken the image and applied some filter and got the horizontal images, right? We have taken the image and we have applied a filter, we've got blur. Okay, and we have taken an image, we put a mask around it, right? So filters basically allow you to extract latent information out of it. Okay, our job is machine learning. What we have to do is that we have to learn the best filter that gives us. What is the best filter that you can achieve out of a network? So what it does is that it does exactly this thing, right? One after the other, it will go and look for all of these things. By the way, there's a term for this going of this one after the other thing. It's called a stride as one. Okay, how much stride are you going? Whatever we just explained is called a stride. Okay, stride is represented by a notation by called as S. You can say that why do stride 1, do stride 2. If you do stride 2, what will happen? It will jump. After it does this once, it will jump 2 cells and it will do the convolution operation. Okay, and then it will come down and it will do the 2 cells, right? Stride, understood stride? Yeah, I mean, you can always say something like this. Okay, stride is something that is clear to you. Stride means that this operation of are you jumping or are you continue to do in a sequential manner. How much should I jump? By default, I showed you a stride of 1. You can actually have a stride of 2, stride of 3, whatnot. Higher stride means you're gonna skip things. You're gonna skip rows and columns of images and move to other sides of it, right? So that is a very important thing. Stride is a very important understanding that you have to understand. So stride 2 will tell you that it will shift image and it will produce a smaller filter, a much smaller filter. If you have a stride 2 for a 3 by 3 filter on a 6 by 6 image, you will not produce 4 by 4 image. Instead, you will produce a 3 by 3 image. I think it's going to produce a 3 by 3 image because you have lesser, you are condensing the information less. Okay, this is exactly what we went through, right? This is like per element wise multiplication, and at the end of it, if you apply many filters, if you at the end of it, if you apply many filters, you end up having lots and lots of features. So essentially, this convolution operation that we talked about, the output of convolution operations are nothing but features. Aggregatedly, they are called as, this term called as a feature map. You will be having two or many such two 4 by 4 matrices if you apply many such filters, which can be termed, which is nothing but a collection of feature map. That is very important for you to understand. Okay, and this feature map is holy grail of everything. Okay, these feature maps are so important, and it not necessarily that you have to do one convolution operation. You can have n number of convolution operation. Okay, let's go back to that first of our images. If you remember, now if you look at that VGG net, do we remember this architecture, VGG net, right? VGG net has 16 layers. You see, the image comes in, does one convolution, two convolution, and does something else. We will look at this, what is pool, okay? And then one convolution, two convolution, do something. So it is just so many convolutions before it does started producing probabilities. Like so many, 1, 2, 3, 4, 5, 6, 4 or 6, 7, and 3, 10, like 13 convolution operation. More you convolve, image shrinks, and you have very refined sort of features. Think about this convolution operation on 152 layers, right? It's almost cleansing the main image at a extremely granular level and getting everything. It just knows the image left, right, and center, right? And it turns out these features are so good that many a times what happens, these features are stored, and this becomes your backbone of many of these things, because the understanding of an image is very open-ended, general. It becomes a general knowledge information. It becomes a common knowledge. We will discuss that. Okay. Okay. Sorry, I'm just going up. So let's go back to our convolution operation, and what we do is like we generate a feature map, right? This problem we'll do it at the end once we come back after the break. Okay. So so that is what it is. So after the break, what we'll do is like we'll look at this thing called as pooling. What does pooling gives you? Okay, why pooling is needed, and we'll try to formulate. We'll try to formulate an equation of what will be the shapes and sizes. Okay, they will discuss some of the things, and we'll try to find out what is the shape of every time you do it. The problem is there is no problem. The essential thing is that we need to understand as a human being what will be our shape and size of each of those layers that we actually generate, right? So we will actually look at that part. In fact, we'll also look at pooling from a pooling is very simple. Again, you can see this after convolution, you can do a pooling. Pooling basically shrink the image more. There are three types of pooling. After that, you can do flatten and present it to dense layer. We will look into that pooling after we come back. But what I'm trying to say is that do we understand till now what is CNN? That is what is. Do we understand the nuance of it? Why CNN? And why do you think this kind of operation was difficult on a dense layer? Because think about it, the image quality is going increasing, right? The number of so in our case till now what we are doing, MNIST has only 28 by 28, and we 28 by 28 was only 784 features, right? Per example was 784 features, and that to one. So now, in higher class, normal natural images are how much? Like, this is like 2-3 MBs, like, which is like, 1900 by 1900, 3-4 channels, right? That has a lot of dense information, right? So if you, and the features are getting exploded. So just normally just passing into dense layer will cause that issue of extremely large dimension. You need to train it for a long time. Okay, and it's going to be very difficult. Plus, all parts of images are not same, and convolution operation, if you see this convolution operation, just be very clear, this convolution operation allows us to create a better feature map. And what we do is that on this feature map, we do prediction. All we do, so all we do as a part of convolution is that we build these features. So convolution in a way is feature engineering of images till the point we actually do prediction. So you use convolution to generate extremely awesome features. Then you pass it to your dense layer for doing your prediction and so on and so forth. The prediction part is anyway simple. That we already know, right? We pass it to dense and do a loss function and so on and so forth. But convolution or the CNN part is where we add all these various types of filters, get a feature map out of it, and and then move on to do the prediction part of it. Okay, I think do you want to take a break? I know we are breaking 5 minutes early, but let's take a break, I say. Okay, come back in 15 minutes. Um, okay, I think that's fine. Okay, let's come back. Let's come back in 20 minutes. Sorry, no, 9:26, right? So 19 minutes and resume our topic. Okay, guys, thanks a lot. Okay, let's resume. Are we back? Okay, right. So we saw that. What did we saw? We saw that the this operation called as convolution helps us in creating good feature maps um, out of each of the images, and we our objective is not to hard code these filters or this convolution operation on the or the filters or kernels, rather than to learn them, right? And we have looked at the various types of filters. Till now, what we did is that in this case, we have looked at a one channel image with a one channel filter. But if your channel is three for an image, you also should also have a filter of three channels, right? And then you should have so many, and you can also have one filter is of three channels, which will make it anyway three dimensional, and then you can basically have as many filters that you want, which when we run the convolution operation, you know we will have something like this, like lots of feature maps, and then that can be used in our this thing. So let's look at one more important layer. While convolution, how do we do convolution in a neural network? We will actually, it's a special type of layer, just like dense layer. We will actually see that convolution is a new layer type. Okay, so if we actually go to TensorFlow, let's go to TensorFlow and let's search for, I don't know. So let's search for conv2d, right? So you will see that convolution 2D is a layer inside Keras layers, and it makes sense, right? Just like any other layer, you can see that it's a filters, and we can specify the size. If you see some sample code, it looks something like this. Okay, you can specify how many filters and each of the filters of how many size, and you can specify the activation function. As with anything else, you can actually wrap it via multiple types of activation function. But this is, most of the things we'll use ReLU, right? So this is very simple. In Keras, it's just one line of code. All these things from a software engineering standpoint, you don't have to worry. You can, you can get away with it because Keras handles the maths part of it, right? So what we should do now is let's look at this. So we have looked into this. We have spoken that if a image is of three channels, you also have at least three channel filters, which will result in a shape like this. I think now you are trying to you will appreciate the fact that why do we have these objects called as tensors, which can hold multiple types of matrices at the same time, right? If you don't have tensors, imagine what would have happened, right? To holding all these multi-dimensional objects at the same time and doing the computation. You need to write a lot of if for underscore for loop, right? Matrix multiplication or tensor computation makes this thing much, much simpler, right? Okay, understood? So let's look at, one thing we also looked at was stride. Okay, what was stride? Stride was, if you, where did we discuss stride? Stride is not here. Stride is something that we discussed here, that if when we move from sorry, if we actually go from here, it's basically, this is a one-sided operation. You can choose to actually make it, yeah, stride is nothing but how much shift you are doing vertically, and at the end of every vertical row horizontally as well, right? Stride is, in that way, it is important. Okay, let's look at one more concept called as pooling. Okay, pooling, what it does is that it gradually reduces the spatial matrix of each the size of each matrix within the feature map. Okay, there is, it's a part of subsampling. Do you remember what was subsampling? You know, subsampling means, you basically reduce all of the images, all of the information without losing information, in a way that, so the information is not lost, however, the data is compressed, right? So that is what is nothing but pooling. The moment you say pool or pooling, what do you do? Like you do carpooling, right? Your destination remains same. You take all of them together, right? Similar concept that we can do in convolution, in image processing as well. Again, pooling is a separate layer. I can show you how the pooling layer looks like. It's fairly standard, straightforward. You have max pool 1D, 2D, 3D. Okay, since we are looking at con 2D, let's look at max pool 2D, and let's look at it is basically, you can see that simple, size. So what does pooling does? This is how we do pooling. Okay, so now that this was our original image, we applied a filter, we've got a convolution block out of it, and on the convolution block you can apply pooling. Pooling is like this. Pooling will do that. You can say that I'm going to apply. So this is a pooling of 2 by 2. Okay, you are applying a pooling of 2 by 2. All you are saying is that take every 2 by 2 block of my output, of my input, any input for that matter. You can pool your original image as well, but generally what happens, you pool the conv output, the feature map of the convolution layer. Okay, so as to reduce the information a little bit more, in a sense that your feature space also decreases, however losing very less information, right? So if you apply a max pooling, yeah, so this is how it is, very simple. If you apply a max 2 by 2 pooling, what it will do is like, it will consider this is a matrix, max pooling, whichever is the max of the fourth thing, that is what it will assign to. As simple as that. Okay, if you are applying a 2 by 2 matrix, one more time, take the 2 by 2 matrix here. Okay, yeah, take the 2 by 2 matrix here, right? Not ReLU is 0 or anything, right? This is just maximum of all these 4 objects or the 4 values. So in this particular 2 by 2 matrix, in the convolution 4 by 4 matrix, I see that there are 4 values: 272, 231, 220, 195. In a way, it says saying that since 272 is the maximum size, take this, ignore others, because this itself will, the reason it is 271 is because the most of the information is of the image is here only. That is what it sort of represents. Okay, so it will condense this information for the maximum number that it can find and put it here. Okay, similarly it will do here. If you see 364, it will slide it 1. Okay, of course this is, so this is done via an activation function. Okay, this will of course will be done via an activation function, and we can see this, right? If you actually go to, it's gonna be done via a layer. Okay, so this is the layer. Okay, there is no activation function here, right? So this is not non-linearity. You're condensing the information. Your objective is to condense the information, but it's very simple, right? Apply the stride. You can say that max pool 2 by 2 of this 4 by 4 image, it will reduce it to a 3 by 3 matrix, and each of these things is nothing but the max of that particular block, and you just do stride by stride. Here also you can specify stride. You can say don't pool for every such 2 blocks and shift by so many number of points. Okay, it has been shown that after every we can, yeah, so can we not apply convolution? Yes, absolutely. Yeah, if you see this. Okay, now that you have understood, I will show you. Okay, we will go to that VGG16 image again, and you will now be literate enough to read that image, that model architecture. Okay, so pooling is nothing but that. There is one more type of pooling which is called as average pooling. What does an average pooling of 2 by 2 will do? It will again apply the same 2 by 2 matrix in this. However, it will do an average of all the full numbers. Average is nothing but add all the number divided by number of the numbers, right? That's all it is. Okay, nothing complicated, fairly simple. The intuition again is that you're trying to take the good parts of all the number and assigning it. Reducing it, you are reducing the number, you are reducing the overall matrix, but trying to keep the sense out of it. It has been observed, max pool just works better than average pool, okay, historically, right? Understood? I think the concept of pooling is understood. Are you able to are you able to understand what is pooling? Now that we have understood what is clear, now let's look at that VGGNet. The question is that can we apply convolution after pooling? After that, we can apply convolution. Of course, that is the whole nature of the game. Now you see VGG 16 layers, right? This is a 16 layer network. The raw image goes in. First thing that it happens is convolution. We are very tuned to putting a dense layer, right? Remember, from the input layer directly it goes to convolution 1. Okay, and if you want, we can actually open up the actual architecture to find out how many such neurons and so on and so forth, right? Each of these also will have neurons, right? So there's a one convolution operation, another convolution operation, back to back two convolution operations, then a pooling. Again back to back two convolution operations, then again pooling. Back to back three convolution operation, again pooling. Three convolution operation, pooling. Three convolution operation, pooling. Okay. So many, so you can see this, right? So image has been transformed, at least 13-14 times, and every 2 or 3 times there is pooling to ensure that you condense the information. And in all of these things, VGGNet uses, I think, max pooling only. It uses max pooling. We'll come back to that. Okay, we are still not done. Why FC? We'll come back to that. But at least at the end of this whole layer of convolution, can we take this image and just discuss? Let me just copy this image, whether it's possible or not. I can. So if you actually take this, right? So just drop it here. Oh, okay, you can't. Yeah, so till this point, till the last pool 5 layer, right? Whatever you have got is the best feature map that all your images have gone through. So at the end of all the pools, you have got the best features. You can make a statement like this: the features that have been coming out after my pool 5 and 5 pooling and 13 convolution operations layers is such a nice is one of the best thing that you will see. Okay, that features is unparalleled, unbeatable, and that is what we presented to our future networks for it to learn. Okay, so right now what we learned is features, and then we have to put it to a prediction. FC is another. Oh, acha. You wanted to know what is FC? FC is fully connected. This is normally the layer that we have seen, which is nothing but a dense layer. Okay, and we need to put this to a dense layer because most of our weights and biases happens there. Most of the information is traveled there, and we have to put it via again a probability function or whatever is there. If you are trying to do image detection or image classification, you need to actually put to a dense layer, isn't it? Your last layer has to be a dense layer by a ReLU function. So, but before that, so many layers of convolution. Same thing. If you actually let's go and see a really large network called as ResNet. Let's do ResNet 50. Okay, and images and don't get baffled by it. But if you see it like this is I wanted to show you guys. So basically the same block. You can see this on the same block. The image comes from the top. Okay, and like 150 layers of after this convolution, so many convolutions. But ResNet uses something called as an average pool. You can see this. This uses now this is actually something, and this like how many 152 layers times 152 times convolutions is network, right? So many types, so many times the convolution operation is happening, and at the end it goes with an average pooling. and then FC is nothing but a fully connected 1000 neuron. 1000 is nothing but that last layer where it is trying to guess this thing. Okay, so that is exactly what is pooling is. Let's not deviate from what we are trying to discuss. We'll come back to what it is. Okay, so now we have done pooling, right? So pooling does exactly the same thing, and what pooling also does is that it honors the stride. If you ask it, you can do stride. At what point? The ResNet people who I think Microsoft, right? They stopped at 152. Um, what is there's another network, right, which went into 1000 layers, right? So it's totally up to you how detailed you want it to be, how much you wanted to know, what is your objective. See, one of the objectives of ResNet and VGGNet and so on and so forth was to create a general vision idea. Okay. Now the thing is that think of like this: a network which is such deep and such understand like this. Okay, it has understand, it has an objective function. The objective was to train, sorry, classify 1000 images. You have given it so much networks, right? And at the last it has given you know at the last, after the average pool, you are passing it for the probability distribution. However, just before that, you have got the best feature of the whole world. What you can do as a transfer learning approach, what is done generally is that they will remove the last layer, which is nothing but a softmax layer, and take the output of just the convolution operation and store that. And that model itself can form your base, because it is considered that now that model is so generic that it can literally classify y thousand millions of objects on its own, right? Because it has already learned features of millions of objects. You don't have to start from zero, you start from millions, right? So so many of these things, there are a lot of benefit to it. And so the one of the transfer learning approach comes from there. And where do we stop is totally dependent on the machine, the model that company is doing. Google's net is a Google's Inception net. It's a really complicated model. I feel that, okay, and it won, right? It won some challenge. The challenge was won. When was it won? So you can see the Google net, 2014, right? Szejewski, the guy who actually Christian Szejewski was the guy who was part of the batch normalization. He invented batch normalization, right? So he was also part of the team who built Google net. It's a very complicated network, right? So where do we stop? It is open-ended question. As long as, so no, we are not trying to reach. We will never reach global minima. Again, remember, we are machine learning folks. We are not optimizing people. Our objective is not to 100% optimize. Then there is a problem. We cannot reach to global minima. We just have to shy away from somehow to global minima. Okay, but we should not. Okay, we should not reach global minima. Great. Let's go back to our pooling operation, right? Now that we have understood pooling, so typically CNN architecture, a very typical CNN architecture, you will see this again and again. You will have convolution operation and a max pooling operation or some pooling operation, okay? But max pooling is generally better. The resultant image is always smaller than the original image, and you will start getting those edges, okay? Those features which can be extremely reliant, and so and very very can create a knowledge base based on which you can build something else, right? Every object in the whole entire world has an edge, right? So how do you detect it? You start from a larger thing and go down to edge, right? So that understanding that there is an edge is something that a model acquires after so much training cycle, and so you can start from there. not never start from zero. That is typically nowadays people do that, something called as a transfer learning. If you want to do something, you just remove the last or couple of layers and you are good with this. Okay. Some more intuition. If you reduce image from these layers, which is nothing but convolution from pooling, is now then passed through some activation function. Okay, whatever activation function you use. Okay, convolution itself is an activation function. Right? It has an activation function, isn't it? And then you can pass it via. So this whole thing is nothing but a convolution layer, and you can pass it via some sort of. So of course we'll have to pass it. So the activation function is anywhere there in each of the convolution layer, right? And that's generally people use ReLU in your Con2D layer itself, right? But this is a classic information, and I think this is also appreciated here, is that, you know, till you can see this image is a very popular image from Stanford, if I'm not wrong, one of those lectures, is that the first part up to pooling, convolution plus ReLU, then pooling, convolution plus ReLU, and then pooling. This is what we are doing, right? Right? Convolution operation plus ReLU, and then we pool, convolution operation plus ReLU, then we pool. This whole part is nothing but feature learning, absolutely 100%. Okay. After that, what we do, we flatten it out. We basically stretch the image into a one vector, right? A kind of a row vector, right? Because each pixel is a feature, we wanted to represent like that. It's easier that way. And then we pass it via our fully connected normal bread and butter stuff. Pass it via some dense layer, 2 or 3 dense layer, pass it via softmax, your image classification is ready. Okay. But the most important thing is that this feature learning is nothing but this part. Okay. This is a very important aspect, and most of the nowadays you can just reuse an existing model to kickstart your learning. You don't have to start from here. You can even start from here also nowadays, because this has already been given by these heavy duty models who has already learned, right? Okay. Let's now look at the last part of the things. We are still not done. A typical CNN is not done yet. Okay. A CNN's objective is not only to learn feature. The CNN part is definitely to learn feature, and after that you have to still predict, right? We are machine learning folks. We have to solve some problems, right? When we are talking about a machine learning, what are we learning, right? A good thing that you are learning the features, but where are you applying? Let's talk about the application part of it. So image goes through some sort of convolution, you create a feature map, right? And that feature map is stretched, okay, and is passed by a dense layer, right? Stretched, we have seen this yesterday as well, remember? 28 by 28 matrix, how did it become 784? It became 784 by something, right? What did we do? Do we remember? We did something. Do you want to go to the, let me just refresh the lab, I think it has gone cold. Do you remember what did we do? Did anybody ran that code when you had time? We did a reshape, right? We reshaped it to a one-dimensional vector. Remember? When we did a reshape, the 28 by 28 two-dimensional structure became a one-dimensional structure of 784 row vector, right? So each of those things are nothing but a pixel which represents one feature each, right? An image feature is nothing but each of the pixels are its feature, right? That's what we represented, and that is what you have to also, sorry, that is what you have to also do. You have to stretch it out. A good thing is that this stretching can be done using a layer in TensorFlow. You don't always have to. In between, you have to stretch, right? It's not possible for you to add custom code, right? Unless you create your own layer. So you can add a layer called as flatten. Okay. Flatten. You want to see what is flatten? I'll show you what is flatten. I think this lab is now causing problem. So if you remember, okay, what did we do? We had, so we did something, where did we do reshape? So X-train scale, we did X-train scale, okay, before that itself, Oh, so this is diabetes. Sorry. So in MNIST, right? So yeah, so you will do something like this, right? So diabetes is anyway, table formula, right? It's a one vector. So this is what we do, right? We always have to do reshape, right? If you do a reshape, the shape of this extent will become 784, right? Similar operation you can do using something called as a layer. There's a layer, I mean OPEF. Yeah. So there's only one layer with the name of F. Basically, it flattens the input, does not affect batch size at all. Right? All it does, its on job is to basically given us this, it will simply make a, if you pass it via convolution layer or something like this, it will stretch it into a one row vector like this. That's all it will do. Right? So this is important for us to understand. Okay. So you have to flatten it, and why we have to do the fully connected part? Because most of our learning, most of our neuron representation happens there. And if you run, most of our weights actually exist there. Okay, right. Fewer parameters. CNN also, if you understand, now the CNN below is only connected to 9 inputs. It's not fully connected. CNN always have very less parameters than any dense layer. In fact, if you run a very big CNN network, you will see each CNN layer will be much lesser. The parameters which are learned at that layer in CNN are much less, but because that's what you're trying to do from a feature point of view, right? And what happens is that most of the things are there in your dense layer, but that is also a good thing because you are not overloading yourself and you have a reasonable understanding of the features. Okay. um, okay, so that is one thing that works good for CNN. Okay, number of parameters can also be reduced. Okay, so you can add a more dense layer. Nobody is stopping you to add more dense layers. You can add dropouts, but you can add regularization strategies after you can add dense layers, right? So max pooling is nothing but a way to reduce things, right? Ensure that you don't have a big, you still continue to maintain the numbers. So max pooling is just one way, though you should not consider this a regularizer, but it still works like that, right? Your sizes comes down. The size of the image comes down drastically. Hmm? We will start. We will start in get hands on. Yeah, just to get basically we will be using our MNIST absolutely without backward propagation. So that is one of the reason, right? So if I ask you to actually what will be the equation of convolution operator, right? You should be able to write it, no? It's a ReLU operation, and inside that you have a W into weights. Weights are nothing but each of the filters, right? And then which is element wise multiplication, which is some product, right? Element wise multiplication with my image, so section of an image, isn't it? And the moment you have those, if you consider them as weights, that's it. So right, that is the reason all of these are functions, because you have to have a backward propagation system. All of these layers has to have a backward propagation system. Each of these layers, right? Whenever you say you have a layer, you must be able to provide a forward pass and a backward pass. It is possible that when you do a forward pass, you might not contribute, you might not have any weight. And do you know a layer which does not have any weight, which does not contribute any weight? Hence, there is no runnable parameter. We saw that. We saw that layer yesterday. Do you remember that? No, no, no. Batch normalization has weights. Beta 1, beta 2. It says hyperparameters. It is, batch normalization actually has weights. Okay. And batch normalization algorithm, if you remember, right, it has weights. What do we don't have? We can see this, right? Let's open diabetes, right? Let's see one of our model summary. Now tell me, can you see dropout? No weights. So your forward propagation says that there is no weight here. There is nothing to learn here. Hence, backward propagation will say that there is nothing to do. No new weight to update, right? So your CNNs also you will have to have weights, right? And your weights are nothing but part of your filters and other parts as well, right? Absolutely. That is a fundamental thing. The question is that if any time you introduce any part of your touch your neural network as a layer or anything, you have to allow it to forward pass. You have to allow, yeah, as a part of your backward prompt, or else there is nothing learning there. You can hard code. If you want the network to learn and not hard code things, right? Then you have to make it a component of a loss, right? You have to be allowed to differentiate against loss, isn't it? And you have to make it dependent to a loss. That's it, which is nothing but a weight. So let's be very clear on that. Okay, great. Code point of view, it's very simple. Okay, it's a 5-line code, like nothing is there basically. It's just as long as you understand this thing, if you remember what we used to do in MNIST, you will see that it is much simpler because you just this that you just it's basically one class, right? And then everything just happens automatically for you, right? So what is multi-layer CNN? That's what we discussed, right? We have many CNNs on top of each other. These are pretty deep CNN. This is the Google net, right? This is pretty deep CNN. You have some previous layers. Each of this, so basically this is any this block is called as an inception block, okay? And there are 1-into-1 convolutions. These are nothing but 1-into-1 filters, okay? So there is 1-into-1 convolutions which goes into 3-into-3 convolutions. And if you are interested to know why, you can read the GoogleNet paper. They have reasons on why they did this, all of this, okay? And each of these blocks are called as inception block. They have, I think, 130 or 140 such blocks. So in each of these inception block has 1, 2, 3, 4, 5, 6 layers. So you can imagine the total number of layers that inception block has. Oh, sorry, the GoogleNet has. So it's a pretty complicated model itself. This won that ImageNet challenge of 2014, right? All of this happening in the 2012 to 2015-16. Remember that, okay? So you can imagine, right, the amount of computation. Again, all of these are backward propagable, or else it's difficult, right? Sorry. So deeper is better. Now I think coming on to a perspective that deeper is always better, right? So we started from 2010, 11, shallow, 8 layers, 9 layers. AlexNet was 8 layers, okay? It used CNN as well, by the way, okay? It had CNN, right? And what Alex did was that he trained, I think Alex only, right? He trained things, each batch on multiple GPUs. He also did some interesting engineering trick to parallelly train things, okay? And then it went to 19 and 22 layer. This is VGG. VGG is a very popular backbone. And then from there it shot to like 152 layers, which is why ResNet, right? ResNet also has 50 layers. So imagine what's gonna happen. So this is what CNN is for us, folks. Let's do one thing. Let us go to our practice labs. Okay. Practice lab is fairly simple. I think you already have. So I assume can you all of you guys go and open your practice lab? Let's go to convolution neural net. Okay. And yesterday I have anyways sent you the image filters. Okay, if you have looked into that, this IPYNB file was already sent to you yesterday only. Okay. So yeah. So let's all of us actually open the. It's a very small assisted practice, and you will realize that if you actually open any one of the older ones, which one should we open? Let us open the, I don't remember what is this. Let's see. No, this is not that one. Let us open assisted lesson 4. Okay, lesson 4. Yeah. So you can see this. So this was the model that we used, right? On MNIST. Again, this is MNIST, right? This is on the day 4 or when we were doing lesson 4. Okay. We ran through the assisted 2, and this is where we introduced Keras, right? Keras, sequential, dense, dropout, and so on and so forth. And we did not use anything of CNN whatsoever. Our model architecture was fairly straightforward. Two dense, and after every dense there was a dropout, and that's about it, right? And we will see a stark difference than this. Okay. What we'll do is, like, let's load our MNIST data. Okay. Okay. Have you guys opened the lab? It's better actually if you open it. If you have opened it, it will be good. Please confirm that if you have opened it. Okay. And let's look at one of the image. Okay. Let's look at one of the image. So this is number 5. Okay. And hmm, will take us, yes. Yeah. After this, we can actually we can discuss. It's a good suggestion. We can do that. Okay. So of course, so this is a shape, right? So of 28 by 28, what are we gonna do? We have to. I'm gonna take this thing, reshape, and then what I'll do is, like, so I will not run this, okay, because it was taking a lot of time. So I will reshape this. Why do I reshape? There was no need for reshape, okay. You can actually, um, yeah. So we should not have reshaped here. Why did we reshape? This should not be done. Okay, because we are giving the total number of images here. Okay, so our shape was ocha. So this reshape was some not flattening. This is giving you a extra dimension. That's what I was thinking. So my X train, what was my X train? It's a two-dimensional 28 by 28, right? Convolutional 2D will have to take three dimension minimum, right? And I have to introduce 1 as my one channel, and 60K, which is my n, right? N signifies total number of samples that I have. So this is what we discussed, and this is what I reshaped. So basically, I gave it two more dimension, okay, instead of bringing it down. So reshape is a handy tool. Why did we reshape? So because our image was 28 by 28, right? Our original data set was this, and to give it a machine, to first of all, to introduce anything to machine learning, I need to add the n, right? Total number of images, my sample size. So this is my sample size I added. And the last one is, because I am using the cond 2D, it requires the channel parameter to be added. So even if it is black and white, you have to add 1. If it is 3, then 3, whatever it is, right? So this is what you have to add. And there is also something called as con 3D that you can use it for one more dimension. You can add it for the videos and all. Okay. So that is also there. So that is the reason we should reshape. So one more time, if you want, if you remember, we discussed about this, right? Where did we write a bunch of things? This is the reason we have to reshape. Okay. The MNIST gives you 3 by 3. I have to go to at least this, right, for my machine learning model to run, right? So this will ensure that all of them are part of my tensor itself. One tensor, I just give it one tensor, it computes for all of them together, right? And it works perfectly fine. This is MNIST, which means this is a classification problem. Which means what? We are classifying. What are we classifying? 0 to 9 digits, right? So if that is what we are doing, and if my, so what do I have to do? This is classification, and it's a categorical, it's a categorical variable, right? So I need to transform my categories into one hot encoded vector. This is very important. Without this, if you don't do this, what will happen? Any guess, guys? What will happen to your last layer? This intuition is extremely important, okay? Without this, your logs function will be totally at loss. Because you said that there are 10 classes, but your Y-train is not in a shape to accept 10 classes, and then your softmax is going to, how will it give you probability? Even if it gives you probability, your loss function will compute with a matrix with 10 probabilities with one scalar value or one basically matrix. Not going to work, right? So you have to give a one hot vector. You have to generate one hot vector, and that is what you give. Remember that, okay? Now let's come to model building. Fairly simple. Build your sequential. Okay, the only thing that we've added is con2D and flatten. Okay. While I am adding con2D is this operation of convolution, and you can specify value. You can see that I am seeing that what is my saying? My kernel size is 3. I am giving it 3 kernels. Okay. So kernel is nothing but list of features, right? So this is what my kernel size is, nothing but my filters. Okay. If let's go back to conf2D. Okay. Let's go back to kernel size is filters. Yeah. So if there is filters, there is kernel size. Okay. So kernel size is 3. So now, there is filter and there is kernel size. Okay. So now if you see, if I do 2, so that I need 2 filters, by default it will be 1. Right? By default this is going to be 1. Right? That means 3 means your kernel size will be 3. Okay? Size of the kernel will be 3. That's all it is. Okay? One filter of 3 by 3. Yeah. Okay. Yeah, one filter of 3 by 3. So let's just be integer dimension of the output space, right? That is number of output space, output filters in the convolution. Okay. An integer or tuple, list of 2 integers specifying the height and width of the 2D convolution filter. What did I give you here? So in this case, it is one dimensional. So all I gave is, I can also give something like this. I can give like this, right? 2 by 2 matrix. In this case, I just gave 3. So it is basically one row with 3 things. That's all it is, right? So basically, the size of this is, what is the size of the filter? It's like this. Sorry, it's just like this. That's it. This is a filter. Okay, that's about it. Right? Yeah, so it's basically 3 size. 3 size, yes. It's just 3 size, nothing else. Right? What is 64? Did we discuss what is 64? What was 64? What is the first value? Do we remember? This is my filter size. So I am giving 64 filters, right? What is my first? So I have 64 filters of each size 3, right? And my second convolution was 32 filters of each size 3. Okay. So coming here, so this is my, like this, I have layer 1, I have 64 of this in my first layer. In my second layer, I have 32 of this. Okay. If they are looking at various aspects of this thing, but it itself looks like, overkill, isn't it? Because your size shape is so small, no point is doing it. But once you do these 2 things, what you have to do? You have got your feature map ready. You can add your max pooling, not a problem. Okay. You can also add batch norm. By the way, batch norm works good with your image kind of a problem. And after that, you must be able to flatten at the last layer. So if you actually go here, after you do max pooling, please flatten and then pass it via dense layer. That is exactly what we are doing here. We'll flatten it out, and flatten it out will give you what? If you actually run this, will it work? Yeah. So now let me just do model.summary. Okay. So you will see something which is very interesting. you'll see that my convolution layers, my first convolution layer's shape is 26 by 64, right? And why it is given a 20 to 20 28 by 28 1, if you actually use a filter size of 3, it will reduce to 26 by 26. 64 is nothing but number of filters that I am talking about, right? And this gives such a low param. See, look at the params. This param is low, even next layer also is low, right? And look at the dense layer. Dense layer is collecting most of my weights. Most of my weight is collected by this guy, the dense layer. Flatten doesn't contribute to any of the weights and biases condition, but this dense layer, like for every class, I will get an output of 24 into 24 and 32, like 18,464, right? That's pretty big. That is what is going. So after my conv 2D, my flatten layer, my flatten, it will actually be a size of 18432, right? So that is how big that. So if you apply a 3 by 1 into 3, 3 means 1 into 3 filter on a 28 by 28 into 1 matrix, you will come up with 26.26 into 1. That's all it is. So what I'm saying is that you have, this is 1 into 3 filter, right? And you have one more which is 28 into by 28, so this is 1, right? This is your original image, this is your filter. If you apply, you will get 1 into 26 into 26. How do you get it? This is the equation which actually can give you that, okay? You have no stride here. This is the equation. I have shown you the equation. This is the equation, okay? So the output of any shape, you can get this equation. N is total number of samples. P is what is your pool, right? Padding, essentially. We have not talked about padding. I don't know why. Let's talk about padding because it's a very important concept. I want to talk about padding and then we should be done. Okay. I don't know why padding is not covered. So we'll talk also padding, and then F is nothing but your filter size. Okay. So the dimension of the received vector can be, N is image size, F is filter, and then you have number of channels, P padding is used, what total number of strides. If you apply to this equation, you will get the final thing. Yeah. No, so it's like, how does it challenge? So let's go see the number 5. How does it? So if you're looking at this part, right, maybe there is a very dark, a very light edge. You are looking at this part, right? This is like each pixel by information, right? So all I'm seeing is that I'm actually taking 1:3 filter and looking at it, right? Even if they are same, many of them might be same, right? This part and this part might be same, but this parts might not be, right? Same to you, same might be for you. How do you define same? Who's same? Your same? Like a human being same or our same? How do you know that it is same? This image might be sparse, right? You take an image which is colorful, right? It will never be same at any point of time, right? Take any of your picture from your phone, it will never be same at any point, right? There will be some variation, even if your pixel is 254 and 255, they still have one number difference. For a human eye, it's impossible for us to understand. You might see that it is same. So this idea, this is the problem that humans face when they were actually try to do feature engineer an image, right, by hand, is that they were using human intuition, but that did not work because we were using our eye cortex. Our eye is not the best way to actually comprehend that very fine differences, right? We have other sensory of instruments. So for machines, it's that one number difference can be a huge difference, right? Even if one pixel is 244 and 250 and the other pixel is 255, we will say both are same, right? You can see that these two are same, might not be same actually, right? So that is what it is. So each of the filters going through it, looking at the part of a very small part of the image and doing that convolution operation, trying to get the information out of it and storing it as a feature. right? Let's do one thing. Let's quickly go to one more very important operation, which is nothing but padding. Okay. So now there's a problem when we do this filter. Okay. The problem is sometimes, if you apply these filters, right? If you apply these filters like this, sometimes what happens is that the edge of the image, the information at the edge of the image might get lost. Okay, and what then is the issue is that again, when you apply a filter, right, the edge, the information that is coming from the edge of the image might get lost. So the typical way to do it is that you take this image, okay, and you suppose you put it here, and you say that I have to pad the image. I'll put some zeros, okay, zeros, and this is called as padding. Okay, so you increase the image in that way. This way, what happens? The image, just the normal size increases and nothing else increases, and so now this becomes your image size. Okay, so what you do is like, so you transform the image to something like this, right? This is basically both same image itself, and but this is a one parrot image. Okay, this is a parrot image. Okay. Generally you always only add 1 0 padding, because there's no point in adding more zeros, right? Okay, TensorFlow on any, I think generally it's always 1 0 padded, right? So now what you can do is like, even if you apply this filter, okay, let's apply this filter. So if you apply this filter, so how do we do it? So equals to max of and some product, right? Some product, right? Of, so this comma. So you can imagine what's happening, right? Comma 0 comma, right? So you understood what we did, right? So this is exactly, so in this is what a parrot image looks like. Okay, where you add zeros just to ensure that you don't lose information from the corners. Okay, sometimes you will lose the information from the corner, and in fact, if you see convolution, so there is the, see, you can see this. By default, padding is valid. So this is a part of your layer itself. Okay, what it will do, it will change the it will increase the matrix by one more. Okay, and basically it just, and then add zeros and then pass it via the convolution layer. It is just, and by default the stripe is 1, so it will do exactly what we did. So this is the intuition behind it. Are you able to understand what padding does? This is exactly what padding does, and then you can generate your normal convolution. The objective of padding was so that you don't lose information at the sites. This is also very important, and by default, see, the thing is this, if you use here, come here in your CNN, okay, in your CNN, you're just given this, which means that the images are already padded, by the way, okay. Somewhere, so what you're saying is that, yeah, exactly. So we were not, so that's what it is. Your corners tends to lose information. You don't want to lose any information, at least corners, right? You want to pass all of them via your convolution operations, right? So strides can lose information if it is more than one. But sometimes padding, what happens is that it's better to actually have this information at the middle, so that you know that, so intuitively it's very clear. In this case you take this, in this case you will take this, right? And intuitively you are looking at a much better image position, right? So you can imagine, right, whether this is good or this is good. You can imagine, right? This will actually, this small part of the image is there and rest at 0. At least the corner is represented heavily. So something like that. Okay. Okay, from code point of view, this is what you do. Okay, and then you flatten it up. Once you flatten it up, you will have you have a fun. Parameters will explode, and the 90% of the 80% of your parameters will be in your dense layers. Okay. Basically, most of them will be in your dense layers, unless you have 152 CNN layers. Okay, like ResNet. Okay, and the rest is normal. Adam, categorical cross entropy, accuracy, train test split, do your prediction, so on and so forth. Rest is just normal. So all this complicated stuff comes down to 2 3 lines. We don't have to do anything, and it just beautifully works. Okay. So that is basically CNN for us, right? If you have any questions, let's discuss. Maybe we should discuss as there was the thing, right? Um, Someone asked that can we talk about projects? Is that what we asked? Or let me just, can you take projects in the assessment lab as well? Can you take as in what do you mean? Oh, take us to the projects. Okay, okay, yeah. Yeah, we can take us. Yeah, have you gone through the projects? So let's conclude. Okay, we have what we'll do, we'll spend 5 minutes on top of it and then we can conclude. So this is CNN, very, very interesting network. We will see what, you know, 99% of all things are like this. However, you should know that, you know, while CNN is awesomely represented, you should know that this new kind of an architecture which uses transformer has also encroached vision, and there's a lot of new types of algorithms that are coming up. Transformer is apparently transform CNN plus transformer or transformer alone also is winning a lot of accolades now. Okay, so this is a very highly again active field of research and competition. A lot of pride is there. Okay, a lot of people have done a lot of things here. Um, okay, got it. Let's talk about projects. Yeah, let's shoot. Let's start asking questions. What is that you want? What do you have in mind? Shova, what do you have in mind? What are the questions that you want to ask? First of all, is this the project that you guys see? I'm not sure whether you see the same projects or. So the first one is what? It's basically an, it's not, right? You have to build a machine learning model. It clearly states, right? Only read the data and so yeah, same, right? So where are you? So this is a house grade house loan data analysis. Good. That's tabular data for you. I don't know how big the data is. You want to see the data? Let's open the data. Let's download the data. Can we download the data? Oh, this is 40 MB, not bad. Let's download it. I have to sign, is it? Oh, this is 150 MB. Right. So let's just download it. It's just 2 minutes. Let's see what it happens. Okay. So this is not a small data, which is good. Okay. You can at least play around with it. It is a practical, which only means that awesome. It's and so that's very good actually. It's a really practical data. So lots of missing values. So from an EDA standpoint, you are saying there are lots of missing values. Do you have a strategy to handle missing values? Please don't delete data just because there are missing values. Try to find out other intuitive way to impute the data. Okay, lost data is always not fill with, yeah, do whatever, but please don't delete it. Then don't drop it. Okay. You can also create a regression model to fill the mean and fill the values, right? Okay. Yep. So if you can do it, and if you want to go nuts, there are other frameworks which already does it. Imputer itself is, yeah, of course. If is there any column where data is 80% more than 80% missing? Any feature? Anyway, 322 columns. What is your strategy of reducing columns? Or have you done your feature importance? Or all the features are important or not? Have you discussed? Have you understood that? So first is to look at the 2 lakh records we are talking about. Sorry, there are 2 lakh records that are missing in some column, and we try to find out what column is that. Then so that has to be something treated. And then you said that there is 322 columns. So which means that you need to find out a strategy to do your feature importance, right? And because I think it will be good, right, if you can actually quantify yourself whether the features are good or not. How are you planning to do it? Anyone? I think find out a way. How will you do it? How will you try to do feature importance? Try, and then did we actually find out whether the data is balanced or imbalanced? Core on 322 will be big problem, right? Think about it. I mean, it's a visual. Then you have to write code. Okay, you can do a see, correlation is not causality, right? You know that, right? Just because it is correlated, that doesn't mean it has caused something. We need to do some sort of feature engineering, right? At least to reduce 322, it feels that you have null data. It feels that you have. I have not looked at the data set. Shall I look at it? Let me. So it feels that there is a scope to reduce the features and try to build a. You can apply PCA, but again remember why you are building a neural network. Remember, not an SVM. Remember that, okay? As long as you have a logic to apply it, you build a proper neural network, okay? Um, but maybe there are some, maybe 100 odd features are really no. 300 features is sounds lot, okay? From a tabular data point of view, okay? Is the data imbalanced or not balanced? Have you checked? Is this housing loan data analysis? Is this highly imbalanced? Okay, so you need to have a mechanism to make it balanced, which means you are basically increasing the data. So I'll look at it. I think it is taking a long time. All right. I will look at it. So what will you use? Someone said Smote, right? You can use Smote to check. This is a tabular data anyways, right? But before Smote, yeah, so 322 columns, we have to find out which are imbalanced, right? How many are imbalanced? See what you can do. Okay, I think Smote should work fine. Then have you thought through what will be your network architecture? There are like how many layers and how many neurons to start with? How many layers and how many neurons to start with? What will be your mini batch size? What will be your epochs? You will definitely yeah. So this is a highly imbalanced data. Of course, right? People who will not be given loan will be higher than people who will be given loan, right? That is expected, right? So as a part of your cross validation, you at least ensure that there is some sort of resampling done, right? So you can use the strategy as well. Now, have you thought about what will be your, um, what will be your, yeah, so network architecture? Think about it, okay? Think about it. I think we start from that point of view. How many layers? How many neurons? What is your each epoch? Generally give 128 per millibyte. That is an accepted figure. Run lots of epochs. Okay. And if your practice lab is not able to handle it, I don't know whether it has GPU or not. You can run it in Colab, but I think it's better if you run it in practice lab so that everyone else can actually debug it. But if you are all fancy and all, if you want, you can actually run in Google Colab as well with the GPU on. Okay, so that is also there. Yeah. Um, yeah. So 3 lakhs. So that is 300,000 data. Okay. 122. So it's not 322, right? 100 and no. So I think it's so columns are 122, right? So what you sorry, yeah. So there's yeah. So this is df.info, right? df.info is correct, right? This is output of df.info. Yeah. So this is fine, right? Yeah. So df.info will not tell you. Really big, hence it is not, it is truncated the information, probably. It is fine, right? You don't need too much information. So, but there are 122 columns, not 322 columns. The features are 122, not 322, right? So let's be clear on that. The df.info that you have set shows 122 features, not 322, right? And of course there are, yeah, df code and so on and so forth. Let's discuss it tomorrow when you guys come. Like what I'll also look at it. I'll find time to look at it. And what will be your architecture of the network? Okay. And yeah, how do you handle data imbalance? 300,000 and data. This is like highly imbalanced, right? Like really highly imbalanced. Right. So neural networks works good on an imbalanced data. You can answer this. If you give your data as imbalance, will it work or not work? I think your first model, no, I think it should work. I think your first model, you should not use any mode or anything. Just do a vanilla model and try to find out. Maybe what you can do is like make a small subset of 10,000 or something. Okay, have your basic network ready. Use those principles, right? The principles that it's a multi-class problem. How many classes? Two classes. It's a binary classification, man. Right? So it's a binary classification, right? Which means that, and if your class distribution is like 10 to 1, looks like, right? It is basically 10%. So 10% of 0 is 1, right? So think that by default, if you want to pick, you close your eyes, you want to put it in your hand in the data set. If you pick up 80% of time or 90% of time, you're going to get 0, and 10% of time you'll get 1. That's your general probability. Build the model at least which reaches the basic probability for one epoch. Understood what I'm saying? If you build a model architecture for 10,000, maybe make it 20,000 data set, make it 60,000, amnesty 60,000, make it 60,000, okay? So that in one epoch it should reach this basic probability of 18 to 20 or 19 to 10 kind of thing. Once you reach there, you have reached the non like normal natural order. Then you can improve on that. Okay, maybe that could be a good starting point to work on. I hope you understand what I said, right? Excel file, yes. So Excel file is, I can share the link. What is that? So Excel file, let me download the Excel file. Okay, that should be fine. Notes, notes I've already shared yesterday. These notes are all shared. Okay, if it is not shared, let me know. I think I have sent a zip file also yesterday. Remember that. So it's all there. Okay, um, including all the assisted notebooks as well. Okay. So tomorrow what we'll do is like let's discuss tomorrow what are we doing. So tomorrow, so this is one, and then there's one more. This anyone looked at lending club loan data analysis? Well, this is a lot of this thing as well. And plate classification. I think what you can you can also start project number 3, which is CNN. Okay, and it's because it's nice. The thing is that it's a plate classification problem, and the model's architecture was already given, right? You have a convolution layer 1 with 32 filters of kernel 5, pooling layer, conv layer, pooling layer, dense layer, dropout layer, right, and predict layer. So you can also, do this, right? You can also do this, right? So all three projects are doable. I strongly suggest please start so that we can have these discussions in a meaningful way. Yeah, so this is also, this is given to you. The answer code is already given to you. Okay. And on loan data analysis, in all of these things, please apply Keras Tuner, and so on. So Keras Tuner, please apply Keras Tuner for hyperparameter tuning. Okay. And yeah, maybe for explainability also you can add, but Keras Tuner you would need. Okay. Lending club loan. This is also tabular data, feature transformation, and yeah, good. I think yeah, then these are good stuff. I think yeah. I think what you need is to be little bit more serious about the projects, because this looks like a good projects that you want to work on. Okay, awesome. I think is there any other questions, guys? Tomorrow, let's talk about tomorrow briefly. 2 minutes. I think we are almost done. Right? What are we going to talk tomorrow? What are we going to discuss tomorrow? Today we finished CNN, right? Tomorrow we will start recurrent neural network. Okay, awesome. So we'll talk about recurrent neural network, and I don't know whether we will be able to finish it or not, but we'll attempt. We will not attempt to finish. We'll go it as our pace takes us, and we will see GRU, LSTMs, okay, and yeah. So we'll mostly focus stays on the time series style of things. 90%, and we'll also talk about this this data called as sequence data. Till now, we were talking about tabular data, and structured data. We will now literally talk about what is this sequence data. Okay, tomorrow's session also will be important and interesting, and we will also find time to talk about the projects. Okay, let's do that as well. Okay, folks, I think let's call it a day. We are, I'll update, yeah, sorry, I'll update, yes. I will update the notes. For which notes? Oh, you're talking about the Excalibur notes. Ah, fine, I can do that, not a problem. Okay. This is nothing, this is all scribble, by the way. Huh? If there are typos, guys, please excuse me. This is something that when I write, I just write. Okay. But while I'll put it. Don't worry. Okay, let me actually do it now, so that okay, guys, I think have a great night if you are in this part of the town or world, and good day wherever you are, and see you guys tomorrow. Okay, thanks a lot. Thank you. Good night.
Thank you, sir, for an amazing session, and thank you everyone for your participation. Please provide your feedback in the feedback link, which I've already posted in the chat box, and I'm posting it again. Please do rate us 5 if you really loved the session. For anything less than 5, please provide your valuable comments there. Thank you, everyone. Have a great day. Bye-bye. Good night.